Hello, we're going to start working on Lab 6, Saturation and Atmospheric Stability. And we're going to start with working on questions 1, 2, 3. And so question 1 says that you're going to use table 6.1 to find the saturation mixing ratio of an air sample A and air sample B. And if you look right down here, this is sample A and this one's sample B. But I'll clean those up so that we can read the numbers. And sample A is 10 degrees Celsius. And so if I flick page, I can see table 1.6, and I'm looking for 10 degrees Celsius. And that is down here. And it's the same thing that you were doing in the previous lab. You're just looking it up off the table. And the answer is 7.762. So I'm going to flick back. And I would write in my 7.762. All right, so you look up yours for sample B with the temperature of 38 degrees Celsius, and then we will start working on question 2. All right, I'm going to work sample A for question 2, which is what is the mixing ratio value of sample A and sample B. So I'm going to do A, and then you're on your own for B. And we're going to use the same equation that we were using in Lab 5, which is relative humidity divided by 100% times the saturation mixing ratio will give me the mixing ratio. And we had looked up the saturation mixing ratio, and down here they told me the relative humidity. So it's 75 divided by 100 times by 7.762. And that will give me 5.82, and it has 1 5, so I'm going to round up to 2. And that would be written in here as 5.822. And you're going to work question B. So for question 3, use the temperature and mixing ratio data to plot the air samples on figure 1.6. So on the next page will be that same figure, and we're going to put in the dots, and the 2 pieces of information I will need is my mixing ratio in grams kilograms of 5.822 and my temperature of 10 degrees Celsius, and I can put that point on my graph. So I'm opening up my graphing, and I'm going to put a big old dot at 10 degrees and 5 grams per kilogram, which would be about here on my mixing. And I'm going to be good and label A so that I know. And you guys can set up your dot for B and label that. All right, so before we start question 4, we want to read this little paragraph that says, assuming that equal parts of these 2 air sample masses mix together, the resulting temperature is halfway between 10 degrees Celsius and 38 degrees Celsius. The mixing ratio is halfway between the values that you found in the 2 samples above. So question 4 has you plot. Question 5 asks what's the new temperature of sample A if it was mixing with sample B. And the 2 temperatures were 10 degrees Celsius and 38 degrees Celsius. So the key is to find the temperature in between. And so to do that, I'm going to subtract my 10 degrees from my 38 and give myself 28 degrees Celsius. And then I'm going to divide my 28 degrees by 2. And that'll give me the halfway between 28, and then I'm going to add back the 10 degrees. So I'm dividing by 2, and that'll give me 14. So I'm just kind of working down. I'm going to write it over here, 14 degrees. I'm going to add back the 10 degrees, and that'll give me the number halfway between 10 and 38. So that halfway number will be 24 degrees Celsius. So the mixed ratio number is 24 degrees Celsius. What's the new saturation mixing ratio? Well, that we're just going to look up in this table right above. So at 24 degrees Celsius, I'm going to look up my number for 24 degrees Celsius, and you can just write that in. 7 is to find the new mixing ratio. Now the new mixing ratio is going to be the number halfway between the numbers that we found on the previous page. So those are the answers that we found on this page under mixing ratio in part 2. You're going to find the halfway between the 5.822 and the 33.286. And I will let you guys have a moment, if you'll pause, to find your mixing ratio, and then we'll talk about relative humidity when you've found your mixing ratio. All right, so now question 8, find the relative humidity. So we found the mixing ratio. We looked up on the table the saturation mixing ratio. This is exactly what we were doing once again in Lab 5. We're going to find the relative humidity. And to do that, you're going to put the mixing ratio and divide that by the saturation mixing ratio and times this answer by 100. So you're going to take the 19.554 and divide that by the 19.210 and times that by 100. Your number will be bigger than 100, and it should be, because this mixed sample is going to be super saturated. Alright, so now I divided my numbers and times by 100, and I get 101.7, and since it's a percentage, I can round to the nearest whole number, so I'm going to round up, and I'll get 102% relative humidity. Remember your units. Question 9 asks you to plot your new point, this new mixed ratio, this sort of like point C, which will be a mix between A and B at the temperature of 24 degrees and the mixing ratio amount of 19.554. And to explain, what do you think determines what's happening in this little reaction? Once you write a little sentence on what was going on for question 9, we can move on to question 10. So now we're going to start talking about adiabatic lapse rates. Now you remember on one of the first chapters that we covered in class, we talked about the environmental lapse rate, the ELR, and we said that it had a natural lapse rate. Now we're going to talk about parcels of air that are rising. So this is the stuff that's going to make a cloud, not just the normal stagnant air. The ELR is the normal stagnant air. Now we're going to talk about the adiabatic cooling, the air masses that are coming down, and we're going to start with what's called the dry adiabatic lapse rate, or the DALR, dry adiabatic lapse rate. And there's an understanding lapse rate, and that is that the temperature will cool 10 degrees Celsius every 1,000 meters. Or another way to think of it is what's written right here, which is that it will decrease 1 degree Celsius every 100 meters. So for question 10, they ask you to calculate the change in temperature for this dry adiabatic lapse rate if your starting temperature is 35 degrees. So if my temperature is going to cool off at 1 degree every 1,000 or every 100 meters, if I'm at 35, at 100 meters, I'm going to be 34. At 200, I'll be 33. At 300, I'll be 32, etc., as I get colder going up. So this is pretty easy, straightforward, and the next step will make it a little bit more complicated, but I'll meet you on that one with video 2.